My name's Aran, and I'm an AI engineer at Amazon AI. And I'm here to talk to you about deep learning on the edge with Apache MXNet, backed by AWS services. So when you hear Amazon AI, what do you think? Well, you might think of our friend here, whose name I won't say because there's one in the room, she'll wake up. And, you know, the ecosystem of products around it, so the Echo Look, the Echo Show, the Kiva robots that we have in our fulfillment centers as well, and also the Amazon Go store. If you haven't seen this, this is a very cool concept that we have now running in Seattle, where you can actually walk in to a store and it uses cameras to track your face, and you can just take things off shelves and leave, and it'll charge you automatically. So what do all of these use cases of AI have in common? Well, one thing that you might think is, well, they all use deep learning somewhere. These deep neural networks that are actually taking inputs, and largely in this case it's going to be visual inputs, and mapping them to outputs that are used by the system to do something. But another thing that you might notice is, actually, a lot of these inputs are being generated at the edge. They're being generated in the store where the cameras are. They're being generated in the home where you're speaking. And the outputs as well are also being processed at the edge. So what Alexa says back to you, that's happening on the speaker. The actual charging of the person when they walk out of the store can actually happen locally in the store. So a natural question arises, well, we have deep learning, and we have a lot of the data being produced at the edge, so why not stick these deep neural networks down on those small devices at the edge? And that's kind of the core question that we're going to explore in this talk. So let's get into the meat of things. Why would we actually want to run deep neural networks at the edge? And the natural question comes up, especially with me being from AWS, well, you have this gigantic cloud, and almost every device in this room is connected to it, so why? Why even bother? We have infinite compute capacity, and we have pipes up there, so why do we care about running deep neural networks at the edge? And the first thing that comes up is latency. You can't beat physics, and the speed of light is going to be fixed. So you essentially need some way in applications where you need low latency to actually do the processing on the device. Connectivity is another big one. When you're not in a reliably connected space, if you're in an autonomous vehicle and you're up in the mountains and you don't know if you're going to be able to talk back to the cloud, you're actually going to need some sort of local processing at the edge. The next one is cost. So those networks that you're using to connect back up to the cloud, those are really expensive. And sending a video stream over an LTE network will cost you a pretty penny. So in the case that you actually want to reduce your costs, you may want to actually be running these networks at the edge. And then the last but not least is privacy and security. In a lot of use cases, there are policies and restrictions that actually require you to keep data on premises. And for that, you might want to be doing some local processing at the edge. So let's go through some motivating examples. Let's start with a fun one. If you've ever seen the Facebook app and the camera on the Facebook app, this is actually one that's actually implemented. The neural style transfer, which is essentially a way a deep neural network can learn a style from an image and transfer it in real time onto another image. And it makes fun filters, and you can send silly pictures to your friends using this sort of technique. Another interesting technique of deep learning running on the edge is in industrial IoT, and things like detecting leading indicators of failure with out-of-distribution detections. That can be done by using a deep neural network on devices and on sensor networks actually running at the edge. And then, I don't know if you've seen this, this story from Washington, D.C., where a security robot fell into a water fountain, but security robots and more generally robotics is another big use case, because you actually want to be reacting in real time in the robotics field to objects and events that you see in the space around you. And then last but not least, what great talk on deep learning at the edge is not complete without autonomous driving systems. And these things are the epitome of deep learning at the edge, because you need to react in real time. You're in highly unstable environments where connectivity could change on you, and people's lives are on the line. So it's really important to get deep learning at the edge right here. So where's Amazon AI in all of this? Well, in Amazon AI, and more specifically in AWS, we want to put artificial intelligence in the hands of every developer. And we operate at every level of the stack, from the high-level APIs and services like recognition and Lex and Poly, all the way down to the GPUs.
that actually power this whole thing, as well as the IoT devices and the CPUs. So what we're going to focus on in this talk is really these lower levels of the stack, which is where deep learning at the edge actually is enabled. And we're going to be talking about all the work that we're doing here at Amazon AI and with our partners on the Apache MXNet product to actually enable this for customers. So why Apache MXNet? And if you haven't heard, Apache MXNet is a deep learning framework that is a collaboration between a lot of universities and industry research labs that Amazon has now adopted as its deep learning framework of choice. So let's dive into why we think Apache MXNet is a good framework, especially when you see so many other deep learning frameworks out there. What do we think differentiates Apache MXNet, and what do we think makes it great for deep learning in general, and very specifically deep learning at the edge? Well, Apache MXNet has three kind of key differentiators. Its flexibility, its portability, and its performance. So let's talk about its flexibility. As you can see, Apache MXNet has a very performant core library, but you can interact with it using Java, C++, Python, JavaScript, Scala, R, Julia, really any programming paradigm you want. So it has this broad base of different languages that it supports, and no matter how you want to program, Apache MXNet has the interface to support you. Beyond that, Apache MXNet actually offers one of the most flexible programming paradigms of any deep learning framework out there. You can actually interact with it using this imperative interface, which looks like NumPy. It looks like you're writing mathematics, basically. Or you can use a symbolic interface, which a lot of people who've used deep learning frameworks like Keras and TensorFlow might be used to, where you're actually building layer by layer. And the exciting thing about Apache MXNet is you can actually mix these interfaces. And we'll see some of that later in some of the code examples that I'm going to show you. So this flexible programming paradigm is another big reason that we chose Apache MXNet as our framework of choice. And performance is another big one. Actually, we are one of the most performant frameworks out there. And in terms of training time, we scale linearly with the number of GPUs that we throw at a training problem. So we've actually tested this up to 256 GPUs and gotten linear scaling in training time. And what that means in practice is your scientists aren't sitting around twiddling their thumbs while their deep networks train. They can just throw more GPUs at the problem, get an answer quicker, and iterate quicker. And that's really important. And the last and most important thing for this talk is the portability of Apache MXNet. It actually runs everywhere. And let's dive into that a little bit more. So Apache MXNet runs on mobile devices, and if you see that link down there, you can visit it and actually get the build instructions for this deep learning framework on iOS and Android. And you can see over here on the left are numbers that we tested on Nexus 5. And while the time is impressive, what's really impressive is the fact that we were able to get the runtime, the actual deep learning core framework, down to such a small footprint on the device. So we're actually running the runtime in under 10 megabytes for these pretty large networks. And the entire app size is actually on the order of tens of megabytes for things as big as an Inception network, which, if you've played around with deep networks, you know is quite a big, beefy bag of parameters that you have to load onto the device to do image recognition and image classification. And you can see an example over here on the left of our deep learning framework running on an iPhone in real time. And this is something that Apache MXNet and its build for mobile devices enables. So if you want to get started with those on mobile devices, there's the link down there to actually get the instructions. Also, Apache MXNet is extremely flexible across IoT devices. And if you go to our Getting Started page here, you'll see we have a devices section where you can find optimized build instructions for things like the Raspberry Pi and the Jetson TX2. So we really support a broad range of IoT devices as well. And one other important thing about Apache MXNet is the community. It's actually the most open of all deep learning frameworks. It's an Apache framework. It has a whole bunch of collaborators, and AWS isn't even the top contributor on the repository. And because of this, we've also decided to choose it, and it's optimized now for AWS. It is actually the best deep learning framework to use on AWS services. So what does this community look like in practice? Well, if you can look here, we have the entire committer graph. This is as of March. And it's only 35% Amazon contributions. We have people from all over industry and academia contributing to this repository, and we're outpacing a whole bunch of other popular deep learning frameworks. And what this actually means is things like our most recent collaboration with Apple on supporting Core ML in MXNet. And if you don't know what Core ML is, it's a recent release by Apple to allow deep networks converted into their specific runtime format called the Core ML format to run really efficiently on iOS and Mac devices. And by simply typing in pip install MXNet to Core ML, you can easily port your models that you've trained in MXNet to the Core ML framework and deploy them on iOS and Mac devices. And this is a collaboration with Apple and a function of the fact that we have such an open framework here that it's really easy for other companies and academic institutions to come in and collaborate and contribute to. And actually, it could never be easier to get started with MXNet. Recently, we've started releasing a bunch of educational notebooks, and if you're a developer who wants to get into deep learning, or a scientist who wants to get into the framework MXNet, if you go to gluon.mxnet.io, we have a whole bunch of notebooks. I think we're over 50 now across the entire spectrum of deep learning topics, from NLP to vision to even generative adversarial networks, which is the cutting edge of research. And they're all laid out in really simple, visual, easy to understand notebooks. So if you take nothing else away from this talk, gluon.mxnet.io will get you started, and honestly will teach you a lot of deep learning that you will need to be productive with the tool in industry. So let's really get into the meat of this talk. Let's talk about running deep networks at the edge and the challenges that you face and how Apache MXNet helps. So what are kind of the unique challenges that we face when we deploy deep networks to the edge on mobile devices, on cameras, on robots, and try to run them in a production setting? Well, when we look at the cloud, where most people are used to running deep networks, it's a really homogeneous environment. We have an x86 CPU, usually a Xeon Intel CPU, and a CUDA GPU. That's kind of the standard stack, and everything is trained and deployed against that. When we get to the edge, things get more complicated. You have a whole bunch of different architectures that you could possibly be deploying on with different performance characteristics. You have a whole bunch of different accelerators, from the Apple Metal GPU to custom OpenCL GPUs like the Mali GPU that comes in a lot of mobile devices. You have digital signal processors, DSPs, that you can use for acceleration. And you even have custom accelerators and FPGAs down at the edge. So this gigantic breadth of hardware that you have down at the edge makes it really hard to understand the environment that you're going to run in. And a one-size-fits-all approach doesn't really work here. And to give you an example of this, you end up seeing this huge performance gap in the types of devices that you're running at down at the edge. On the left here, we have a high-end device, an NVIDIA Jetson TX2. And actually, this device is extremely powerful. It has 128 CUDA cores and looks like the GPUs you run at up in the cloud. So you can just take your networks, generally, wholesale from the cloud and port them down to this device, and you're fine. But then on the other end of the spectrum, we have something like a Raspberry Pi. You have a gigabyte of RAM. It's got ARM Neon instructions for acceleration, which are good, but they're nowhere near the performance of CUDA cores. And it's using this 32-bit ARM v7 processor. So there's a huge amount of heterogeneity down at the edge. And to give you a visual example of what the problem is, this is a classical ResNet architecture, which is something that's used very commonly in image processing. And if you take away nothing else from this image, just take away that it's big. And when you train this thing up in the cloud, it's really easy to deploy because you have that homogeneous environment. But when you move to the edge, it becomes really, really tough because of the fact that you have these relatively wimpy devices that you're actually deploying on. So the question comes up, in the face of that gigantic model, MXNet gives you the power to plug into all of these different environments and run in all these different environments. But the actual model that we are running has to change. It's just too big. No matter how many accelerators we leverage, we're bounded by the RAM, we're bounded by the compute. So we need to start adapting our models to this new world. And how is MXNet helping there? So the first thing we need to characterize when we're thinking about adapting our models is, like any good engineer, think about the cost. Where is the really big cost here? And especially in the vision scenario, convolutions end up being a huge time cost in terms of the number of multiplications you have to do prediction on images down at the edge. And a nice little visual example here shows with just a one-dimensional or two-dimensional convolution, you have about 8 multiply, add, carry operations. And usually the tensor that you put in is really deep, so that can actually quickly explode on you. And the number of multiply, add, carry operations becomes pretty unwieldy to deal with, especially for wimpy processors. And another big cost is the fact that models are generally over-parameterized. You throw way more parameters at these things than you actually need, and that's a function of the fact that the data that you're fitting is really complex. Image data is not simple to understand, and that's why we need to throw tens or hundreds of millions of parameters at it when we're training a model. But the problem is that we get these really high variance models, and we're highly over-parameterized, so there's a lot of wiggle room there for you to actually trim down the number of parameters you're using while still being accurate down on the edge. So let's get into actually solving some of these problems. A really simple kind of order one approach we can take is using something like a cheaper convolution trick. So the Winograd convolutions derive from this idea that convolution in the time domain is equal to essentially a pointwise multiplication in the frequency domain. And kind of the simplest example I can show of this is basically multiplying these two matrices. You can actually split it up, and instead of naively doing this and getting 6 multiply add carries, you can optimize it to actually get 4 multiply add carry operations. And that might not seem super impressive, but think about doing hundreds of these every time you run an image through a network for recognition. And that's a 30% savings. That's a 30% time saving for you. And that actually adds up and becomes really important. And in MXNet, under the hood in our convolution operation, with things like NNPAC and CUDA that actually implement this Winograd transform, we've made this sort of optimization available to you on edge devices. Another important thing is, and this has become popular recently, is separable convolutions. And specifically, we're looking at depth-wise separable convolutions here, which if you're into deep learning literature, you might have read about in the Google MobileNets paper. And essentially, the idea here is that instead of convolving over the entire input tensor, the input image in this case, with 3 channels, and doing that for each individual output channel, you can convolve individually over each of the input channels, each of the RGB input channels, and then put them into an intermediate tensor that you then run a 1-by-1 convolution over. And while that might sound pretty complicated, what it means in practice is you just have to do far fewer multiply, add, carry operations to actually run through this convolution. And the trade-off is you actually get a little bit less of a flexible convolution, but again, this in practice seems to be less of a problem. And because you have GPUs that can run a lot of multiplications in parallel, this isn't always the best thing to do. It doesn't wholesale make your network faster. But if you're running on something like a CPU that can't run a lot of multiplications in parallel, this significantly reduces the number of multiplications you have to do and makes your networks more efficient. And then let's look at some of the code to do this in MXNet. You see down at the bottom is kind of the classical convolution. And up top is our optimized depth-wise separable convolution. And you can see we're using the symbolic interface mixed with the imperative interface here, where we're defining symbolically each of the channels, slicing symbolically along each of the channels, and then imperatively going through doing that convolution with depth 1 on each of the channels and concatenating them into that output tensor. So this is basically doing exactly what you saw in the image in the slide before. Pretty simple in MXNet, and there's a bunch of examples of this online. And we've actually optimized the back end. So when you write this sort of operation, you get an optimized back end out that runs on devices very quickly. Another trick to get fewer parameters is actually quantization. And this is basically the idea of taking these networks that you train at 32-bit size. So it's a FP32 floating point 32 number that you usually train at, and mapping that into a smaller bucket. In this case, we're mainly concerned with int 8, which is an integer 8 representation. So that's a 4 times size reduction in the actual bit width of the network. And this is really good, not just for reducing kind of the representative size of the network, but also good to take advantage of low precision hardware acceleration. Some hardware that you get at the edge actually runs faster when it's multiplying int8 values than when it's multiplying FP32 values, because the bit width is smaller, it can take advantage of more register space, and at the end of the day, it means that your network will run faster. And in MXNet, again, we enable this with these nice quantize and dequantize operations that can map into quantized layers. And you can see here, it just couldn't be easier to quantize and dequantize your networks. You just put in the input symbol, and you get out kind of the buckets that it maps into. And then when you want to dequantize anywhere intermediately in your network, you just put in those buckets again and dequantize. And it tends to actually not hurt accuracy that much in practice. And then another trick that we've implemented is weight pruning. So this is actually, while you're training, you can take the really small values, the small weights, and just snip them away as you're training. And what that allows you to do is actually sparsify a lot of these operations in your deep neural network without hurting accuracy that much. And it can really give you acceleration if you can get to something like 90% sparsity and take advantage of sparse data types, because multiplication, especially for CPUs with sparse data types, is much faster than multiplication with really dense representations. And this is a really cool technique that we've most recently, I think about a month ago, pushed into MXNet. And you can see here, basically, as you're training your network, all you have to do is swap out the SGD optimizer for sparse SGD, which I have underlined there, and then say what kind of weight sparsity and bias sparsity you want. And in practice, sparsifying all the way up to 80% doesn't actually hurt your network accuracy. So this is a graph of a ResNet top 1 error, and state-of-the-art's around 75 here. And we have different levels of sparsity, from 90% down at the bottom all the way up to 0%. And you can see we can get to a really high degree of sparsity, 80% sparsity. That means pruning away 80% of the parameters in that network without hurting accuracy that much. So it's a really powerful technique. Another interesting thing we can do is actually just re-architect the whole neural network from the ground up. And this is a little bit harder to do in practice, and the prototypical example of this is something like a squeeze-net, where essentially we've taken those gigantic ResNet architectures and AlexNet architectures that you might have seen, and we found just a much more efficient representation of them. So it's about 50 times fewer parameters than an AlexNet, and it's good for things like devices that don't have a lot of RAM, because you need to load all the weights into memory at the end of the day. And if you have 50 times fewer weights, it's a lot easier to load them in to a much more memory-constrained device. And how do you get a hold of these in MXNet? Well, we have this gigantic model zoo that you can find on our website, apacheincubator.org/model zoo, and it has SqueezeNet, VGG, ResNet, all the kind of canonical architectures, and a lot of more efficient variants of those architectures, pre-trained for you. And then another interesting optimization you can make, this has actually come out of some research in our lab, is actually doing things like tensor decompositions inside your network. And while that might sound like a big scary word, all it means in practice is essentially when you flatten your parameters or your activations. So right before the last layer of your network that's doing the classification, you tend to want to flatten the output tensor that's coming out. It actually destroys a lot of that spatial structure. And what we found is that we can actually do this in a much smarter way, where we actually learn a decomposition of that tensor that preserves a lot of that linear structure. And so those last few layers that are doing the mapping into the space that's being classified can actually be much smaller, because it has to learn a much less complex function, because we're doing a lot of the heavy lifting for it when we do the decomposition. So the code is actually here at this GitHub link, and you can actually read the paper as well. To get a sense of what we were doing there. And this is also implemented in MXNet. So just to kind of give you a quick overview of these techniques that I quickly ran through, here's a little table on how each technique kind of benefits different parts of model execution, from CPU acceleration all the way down to specialized hardware acceleration, model size, and accuracy. And if you take nothing else away, just understand that this shows that there are always trade-offs. And when you are optimizing your model for edge devices, you really have to understand what the end hardware you're running on looks like to intelligently decide which of these trade-offs you're willing to make. Are you willing to give up, for example, accuracy to get a lot of acceleration by sparsifying to 90%? These are trade-offs you have to think about when you are trying to deploy these networks down onto edge devices. Oops. Another interesting thing that you might take away is that all of these edge optimizations actually benefit the cloud. So you can actually take a lot of these techniques that slim down and make networks more efficient and apply them to the networks you're deploying up in the cloud. And what that means in practice is that your compute load actually gets reduced per inference, per image that runs through, because you're using a lot of these techniques to underparameterize and make more efficient representations of your deep network. And what actually is an interesting side effect is that models with fewer parameters often tend to generalize better. So if you remember that bias variance graph I showed before, by actually reducing the variance of your models by removing parameters, you often tend to get more accurate models, which is a little counterintuitive, but in practice, that's actually the way it tends to work. Another interesting thing that goes all the way back to the introduction is that when you have a lot of data being produced at the edge, having small neural networks that are doing things like filtering and intelligently deciding when to escalate to the cloud can actually save you a lot of money on cloud processing. Because you're not running these cloud jobs all the time to process data. And you're doing a lot of that down at the edge where it's being produced. So let's step back and see where AWS can fit into this whole picture, because to this point we've just been talking about Apache MXNet. So the key thing is, when we're talking about all these networks and efficient ways to train them and deploy them with Apache MXNet, you still need to actually go through that training process, which has a lot of challenges. And primarily, the challenge is scale. You just need a lot of data to train these things, and that's no secret. You need a lot of data and a lot of compute. So these are kind of the three big buckets of challenges that AWS provides the infrastructure to help customers tackle. In terms of data, we have S3 and Redshift and all your classical data warehouses, and we also have tools to migrate data up into the cloud, where we have huge numbers of GPU servers and elastic capacity, and we actually are also launching Volta, which is the next generation of NVIDIA servers up in the AWS cloud as well. So we're bringing a huge amount of compute power down to the data that you have up in the cloud to train these networks. And then we also have a lot of services to help with prediction, managing the IoT fleets that you might want to do prediction on, as well as the cloud servers you might want to do prediction on. So let's dive into some of the tools that we have. And the first one is kind of our core base infrastructure, the P2 instances. So if you're actually trying to train networks up in the cloud, you want to actually rent out one of these P2 instances that has GPUs on it and is able to run big training jobs. The deep learning AMI is another big one. It's essentially a quick start image that you can load onto any machine you spin up that has all the deep learning frameworks and things like the NVIDIA drivers and MKL drivers for the CPU already installed. So to get up and running, it's basically just one click, and you have a state-of-the-art deep learning environment. And then the last thing is our CloudFormation templates, which actually let you spin up a whole bunch of GPU machines at the same time and coordinate them together to do large distributed training jobs and let you leverage some of that linear scaling that I showed off earlier with MXNet in terms of training. So the deep learning AMI is probably the most important tool that I've talked about here, and it supports all kind of the classical NVIDIA GPUs. It has Apache MXNet and all the other frameworks preloaded onto it. It also has Python support. It has a bunch of other R, I think, and a couple other languages already preloaded onto it, and it has a bunch of notebooks and examples. A lot of those notebooks from the Gluon repository that I showed earlier will be on that box, so you can actually get started with just learning concepts by spinning up one of these machines. So to spin it up, just go to this link right here, and there's a quick start guide that'll get you set up and running on our deep learning AMIs. So the core thing here with the model that AWS is presenting is that you want to basically train in the cloud where all your data is warehoused and you have access to huge amounts of compute to train these things. But then we want to go ahead and predict on the edge. And while I showed off all of the technology we have to help you train in the cloud, let's move on to some of the technology we have to help you predict down at the edge. So if you haven't heard of AWS IoT and Greengrass, these are two services that we have that you can basically load clients onto any IoT device in your fleet and it allows it to securely communicate back up to the AWS cloud. And using Greengrass, you can actually coordinate fleets of IoT devices together down at the edge and manage code on them and deploy code down from the edge, including deep networks. And you can also monitor their performance as they're running down at the edge. So it's a really powerful set of tools to help you just get that infrastructure in place to manage deep learning in your IoT fleets. And it actually enables these really powerful models now. When you have deep learning plus AWS services, plus Apache MXNet, obviously, and things like this become possible, where you're actually capturing data down on sensor devices like the Raspberry Pi that are running really simple models, and they can escalate to hub devices in that local network, like, say, a Jetson TX2 running a much more complex model. And in the case that you want to actually use some bandwidth and send data up to the cloud, that Jetson can make intelligent decisions about when to send the data from this hub and spoke model down in your network up to the AWS cloud. The AWS cloud, you can actually monitor and manage all of these devices down at the edge. And you also have access to things like our custom P2 model instances that you can load your own custom models onto, and our AI services like Recognition, which is our service for image processing, or Lex, which is our service for natural language understanding. Another interesting pattern where you don't even need to connect to the AWS cloud, but you can just use the Greengrass service, is things like a local learning loop. Because Greengrass enables your devices at the edge to talk to each other, you can actually have devices coordinate and do things like have a small model running on a Raspberry Pi, say, and classifying data and sending the results up to your hub, a Jetson TX2 with a much more powerful model. And that Jetson can actually correct the mistakes that the Raspberry Pi is making, and because it has a GPU on it, it can actually fine-tune the model that's running on the Raspberry Pi and deploy it back down, making the model that's running on the Raspberry Pi smarter and smarter and smarter. So this is a really powerful pattern, and this is something that Greengrass makes really easy to enable because it allows all your devices to securely communicate with each other down at the edge. So if you want a quick start, basically, to get started with Apache MXNet on the edge plus AWS IoT, I'd recommend going to this short link right here where we have a blog post that basically walks you through the process of putting Apache MXNet onto a Raspberry Pi device with a pre-trained model from our Model Zoo, and then wiring it all up to the AWS cloud to actually manage that model, get prediction results back. So that's a really quick and easy way to get started with deep learning at the edge of Apache MXNet. And it wouldn't be an Amazon talk if we didn't mention our customers. We love our customers, and this is just a sampling of some of the customers that are running AI in production today on AWS. Of course, we're hiring. You're probably going to see a lot of these slides today. And thank you very much for taking the time to dive into MXNet at the edge with me.